Imagine stepping into an elevator at the equator. No countdown, no thunder of engines, just a cabin that begins to climb along a ribbon that vanishes into noon sky. The display reads, "Destination geostationary orbit." Clouds thin, blue turns to black, and Earth's curve brightens beneath you. Hours later, you're 36,000 kilometers above the same patch of ocean, motionless relative to the ground because the elevator's track is locked to Earth's rotation. It feels like science fiction. The question is simple and ruthless. Could a structure like this actually work? A space elevator is not a tower. It is a cable held in tension by Earth's gravity below and by the outward pull of orbital motion above. The tether runs from a platform on the equator up through geostationary orbit and then much farther to a heavy counterweight. If the mass and length are chosen correctly, the whole system acts like a perfectly tuned string, always pulled taut by the planet's spin. Robotic vehicles, climbers, could then crawl along the tether, hauling cargo and eventually people. Why try? Rockets are magnificent but wasteful. They throw away stages and burn oceans of propellant just to escape their own tanks. An elevator pushes most of the energy work to the ground. Beamed power lasers or microwaves or solar energy in space would feed electric motors on the climber. No oxidizer on board, less hardware to discard. If it worked at scale, cost per kilogram could fall. Launch cadence could rise, and access to orbit could shift from spectacular to routine. That dream hides four unforgiving pillars. First, geostationary dynamics, the choreography that keeps the tether lined up over one longitude while climbers move and winds shove. Second, materials, a ribbon with extraordinary strength to weight and vanishing defect rates, manufactured not by meters, but by tens of thousands of kilometers. Third, transportation, traction, power delivery, heat rejection, guidance, and traffic rules on a cable that crosses weather, vacuum, and radiation belts. Fourth, safety, fault tolerance, and recovery. When something goes wrong, because in space systems, something always does, start with a dance. In geostationary orbit, a satellite circles once per sidereal day, matching Earth's spin so it appears fixed over the equator. That is why television dishes can stare at one spot in the sky. For an elevator, this hovering makes alignment possible, but balance is the catch. Stop the tether at geostationary altitude and it will not stay stretched. Gravity wins. Extend the cable far beyond, add a counterweight, and the outward pull above geo balances the inward pull below. The center of mass must sit near geostationary altitude so the system rotates as one piece, like a baton spun from its sweet spot. Tension is the art and the agony. Stress isn't uniform. It peaks near geo and eases toward both ends. Engineers answer with a taper thickest where loads are highest, thinner where loads are mild. The math is elegant. The factory is merciless. Your material must be ultralight, ultra-strong, and nearly flawless across astronomical lengths. Tiny defects that are noise in a short sample become lethal in a ribbon that crosses the sky. The environment is a stacked gauntlet. Near the surface, wind shear, rain, lightning, and hurricanes twisting the tether and threatening the anchor. Higher, jet streams, and brutal cold. Above that, the ionosphere, where charged particles chew at materials and spark electronics. Then space proper, vacuum, ultraviolet, and particle radiation, micrometeoroids, and human-made debris screaming past at several kilometers per second. Each layer adds new failure modes. Each demands sensors, shielding, and active control. Travel on the tether looks nothing like a building elevator. A climber grips the ribbon with traction wheels or magnetics and inches upward for days. It draws power from a beam or the sun, dumps heat through radiators, and rides out weather during the first hours. As it climbs, it tugs the cable and launches waves. If speeds and timing are unlucky, those waves can amplify. Control systems must throttle motion to keep oscillations tame. Meanwhile, traffic rules matter. How many vehicles can be on the line at once? How fast can they go without exciting resonances? Where do they pass each other? Then there is the hardest pillar, materials. Steel, aluminum, titanium, non-starters, even high-performance polymers that make bulletproof vests struggle when safety factors and taper are added. The dream materials are nanoscale, carbon nanotubes, graphene, maybe diamond, like threads. In small lab samples, they set records for specific strength, scaling them into defect-tolerant kilometer-class yarns, and then into a continuous ribbon spanning Earth to space, is an unsolved manufacturing marathon. Finally, the bad day handbook. What if debris slashes a strand? What if lightning hits the platform? What if the tether breaks high, low, or near the middle? Hollywood imagines a world-wrapping whip. Reality is less cinematic, but still dangerous. Break location dictates the outcome. Lower segments fall back. Upper segments drift outward. A responsible design uses redundancy, multiple parallel filaments, mesh-like patterns, replaceable sections, and plans for controlled release and guided re-entry, so fragments fall where no one lives. Here is our flight plan for the rest of this documentary. We will map the geostationary geometry and show how the counterweight sets the tune for the whole system. We will derive the taper and translate ultra-strong into real numbers. We will ride with a climber from storm clouds to starlight and study how to beam power without frying the air. We will stress test the concept with realistic failures and see what survives. And we will compare Earth's elevator to easier cousins on the Moon and Mars before offering an honest verdict. Could a 36,000-kilometer elevator actually work, or is it forever one breakthrough away? If the space elevator belongs to science fiction, it is the practical kind, the kind that becomes real when materials and money finally align. If it is feasible, Earth orbit stops being a destination and starts being infrastructure. Either way, the physics is worth the climb. Welcome aboard. The doors are closing. Our ascent begins now. A space elevator stands by balance, not by bulk. The balance lives in geostationary orbit, the altitude where a satellite circles once every sidereal day, about 23 hours, 56 minutes. So it stays over one longitude on the equator. That altitude is about 35,786 kilometers above sea level, and the orbital radius from Earth's center is about 42,164 kilometers. At that ring, gravity and the outward centrifugal effect of Earth's spin match for an object that is moving with the planet. The tether must cross that ring and keep going. Below geostationary altitude, the cable feels more gravity than outward pull. Above it, the outward pull wins. By extending the cable far above the ring and adding a counterweight, the upper section pulls outward hard enough to keep the lower section stretched. The overall center of mass then sits near the ring, and the entire assembly co-rotates with Earth like a baton spun from its sweet spot. That is what holds it up. Only the equator works. If you try to anchor the tether off the equator, Earth's spin drags the base sideways until the line snaps back toward the equatorial plane. The fix is simple in concept. Put the base on the equator, ideally on a mobile ocean platform that can shift a few hundred kilometers east or west to stay under the skytrack and to dodge storms. The anchor is not a pillar. It is a leash that keeps the bottom end where orbital mechanics want it. Geostationary does not mean motionless. Earth is not a perfect sphere. It bulges at the equator, and that bulge shifts orbits. The Moon and the Sun also tug. Engineers call these perturbations. Left alone, they change the longitude and tilt of the system. We counter them with small thrusters near the counterweight, with movable ballast, or with helper spacecraft that pull gently on the top. The guiding rule is simple to state and hard to maintain. Keep the center of mass of the entire elevator exactly on the ring. Climbers complicate the picture. As a heavy vehicle ascends, it must gain tangential speed because higher orbits travel around a larger circle in the same 24 hours. That extra sideways speed is borrowed from the tether and counterweight. The line leans a little west, and tensions shift. If you schedule two climbers in opposite directions, or time departures and arrivals with care, the momentum trades can cancel. Traffic planning is part of dynamics, not just logistics. Air matters only in the first slice of altitude, but it matters a lot. There, jet streams bend the ribbon. Storms try to kink it. Lightning hunts tall conductors. Designers answer with aerodynamic shaping, so wind slips around the ribbon, with lightning protection and with base steering. A sea platform can steam away from brewing cyclones and park under calmer skies. Above the weather lies the ionosphere, a region of charged particles that can charge the tether and interfere with electronics. That calls for grounding paths, conductive coatings, and careful power routing. Think of the tether as a guitar string that can be plucked. Climbers, gusts, and day-night heating launch waves that run up and down the line. If a wave matches one of the natural frequencies, the motion can grow resonance. We prevent that with active damping. Sensors watch the ribbon, small winches at the base, and trim thrusters near the top shift phase and shed energy. The aim is not a perfectly still cable. It is a cable whose motions fade instead of grow. Length above the ring is a major knob. If the tether stops exactly at geostationary altitude, tension at the bottom is fragile. A strong disturbance can put slack into the lower section. If the tether extends tens of thousands of kilometers higher with a hefty counterweight, tension stiffens and stability improves. That extra length gives a bonus. Release a payload from far above geostationary, and it leaves with extra energy, reaching higher orbits or even escape with little propellant. The elevator becomes both a ladder and a slingshot. Longitude is practical and political. Geostationary orbit is crowded with communications satellites in regulated slots. The elevator would claim a narrow lane. We must coordinate crossings and avoid debris. Radar and optical tracking warn of hazards. Some concepts let the tether yaw by a fraction of a degree, enough to let a neighbor pass, then return to center. The margin is small, but good tracking and quick control make small enough. Time sneaks in as well. Earth's rotation rate wiggles by milliseconds because of tides, winds, and interior motions. Over decades, it drifts. Those changes shift the exact altitude of the geostationary ring. The system must absorb that drift by reeling the tether a little and by spending small amounts of fuel on station keeping. These are routine tasks, not daily emergencies, and they show that the elevator is a living system that needs quiet, continuous care. Safe operating margins tie the dynamics together. If the line slackens near the base, it dips into thicker air, drag rises, and the dip deepens a feedback loop. If the line tightens too much, stress climbs toward the material limit. Operators live in the middle by sizing the counterweight with margin, by keeping sensors healthy from sea level to space, by pacing climbs, and by leaving room in the schedule for weather holds. The goal is a wide, stable basin where small disturbances die out. In one sentence, geostationary dynamics set the rules. Build on the equator, pin the center of mass to the ring, extend well above to lock in tension, schedule climbers so momentum trades balance, and nudge the system against slow drifts. Do those things, and the line stays up, not because Earth holds it, but because Earth spins, and the elevator spins with it. A space elevator does not fight gravity by being thick and heavy. It survives by shaping stress. Picture the tether as a very long ribbon under tension. That tension is not the same everywhere. Near the ground, the ribbon feels strong gravity and a little centrifugal push from Earth's spin. Higher up, the push grows while gravity weakens. At geostationary altitude, the two balance if you are moving with Earth. Above that, the outward pull wins. Because the local pull changes with height, the ribbon's tension builds, peaks near the geostationary region, and then slowly eases toward the counterweight. Engineers never want any single spot to be the weak link. The clean way to spread risk is to keep working stress roughly constant along the whole length. That means the ribbon must be thicker where tension is highest and thinner where it is mild. The resulting shape is called a taper. For a space elevator, the math leads to an exponential taper. As you move up, the required cross-section grows smoothly, not in steps. You do not need the equation to get the idea. The ribbon fattens toward the middle where loads peak, then narrows again toward the ends. Why exponential? Because the change in tension with height depends on the local effective gravity in the rotating frame, gravity inward, centrifugal outward, and the material's specific strength, which is tensile strength divided by density. If you want the same safety margin at every altitude, you let the cross-section respond continuously to that changing environment. Integrating that change yields an exponential curve. The take-home: your material and your geometry are married. If the material is barely strong enough, the taper explodes to ridiculous thickness. If the material is excellent, the taper stays modest and buildable. Shape matters in air. The lowest 50 kilometers run through weather, jet streams, and lightning. A circular cable would catch wind like a pole. A flat ribbon slices the flow and sheds gusts. Designers add a slight twist or a subtle airfoil to reduce drag and vortex shedding. Conductive paths and lightning protection live in surface layers. Near the base, the ribbon may sit inside a slim aerodynamic sleeve during storms. None of this changes the core job: carry tensions safely to the sky. Now zoom in on the ribbon's internals. A single monolithic strip would be fragile. One cut could sever it. Modern concepts use many parallel filaments bundled into lanes, woven like a mesh. This multi-lane structure is often called a Hoy tether pattern or a ladder-like ribbon. The benefit is redundancy. A micrometeoroid might cut some filaments, but the load reroutes around the wound. Small repair robots can stitch in new strands while the system stays live. The ribbon is not a rope. It is a highway of fibers with many alternate paths. Climbers need a grip zone. That zone becomes a wear surface. Traction wheels, clamps, or magnetic actuators press on the ribbon and leave microscopic scars. You do not want those scars in your primary load-bearing fibers, so you separate rolls. The ribbon has a structural core for strength and sacrificial outer plies for traction. Over time, maintenance robots replace the worn plies. Think of changing tires without removing the axle. Joints are part of life on a 36 0-kilometer system. You cannot manufacture it in one piece and carry it out the door. The ribbon is built from many standardized segments. Each segment has tapered ends that overlap with the next, so load transfers gradually, avoiding stress spikes. Splices are designed to be inspected and swapped by climbers. The layout anticipates damage: extra anchors for temporary bypasses, spare segments stored in orbit, and zipper interfaces that let you replace a strip without pausing traffic. Tension is not static. Sunlight heats the day side. The night side cools. Thermal expansion and contraction make the ribbon breathe, changing length by meters. Those changes send slow waves along the tether. Sensors track temperature and strain. Actuators at the base and thrusters near the counterweight add or release a tiny amount of length to keep overall stress where it belongs. The goal is to keep stress steady and avoid cycles that fatigue the fibers. Dynamic loads ride on top. A heavy climber pulls down on the ribbon as it accelerates upward and pulls less as it breaks. Gusts, lightning currents, and ionospheric charging can add quick jolts. The tether's geometry must avoid spots where these jolts focus. Smooth taper, smooth joints, and careful scheduling of climbers all reduce the chance of building a standing wave. If a wave appears, active damping phase-shifted tugs at the base, trim jets at the top bleeds it away. What about numbers? Instead of quoting equations, hold on to two plain ideas. First, The maximum tension is not at the anchor or at the counterweight. It sits near geostationary altitude. Second, the ratio between the thickest and thinnest cross-section, the taper ratio, tells you whether a material is viable. If you need a ribbon that gets thousands of times thicker in the middle, you are stuck. If the ratio is in the single digits or tens, you can imagine real factories making it, launching it, and replacing sections on orbit. Material choice drives that ratio. Metals like steel or aluminum are out. Their specific strength forces a huge taper. High-performance polymers do better, but still struggle when you add safety margins. Advanced carbon materials, nanotube bundles, graphene-based fibers, or diamond-like threads promise the specific strength to keep the taper reasonable. But promise is not product. The geometry will not forgive defects that run for kilometers. That is why manufacturing quality and inspection are as central as physics. There is also mass distribution to consider. You do not want all the mass at one height. A well-tapered ribbon spreads mass, so the center of mass of the entire system sits near the geostationary ring. The counterweight above helps tune that. If you extend the tether far beyond geo, the upper part can be lighter than you might expect because the outward pull there is strong. The bottom, inside air, may be wider than the top because of wind and wear layers, even though the raw tension is lower. How do you actually build the shape? You begin in orbit. A seed cable is deployed from a spacecraft near geostationary altitude, one end reeled down toward Earth, the other reeled up to the counterweight. The seed is thin, just strong enough to hold itself. Then swarms of climbers run up and down, laying additional filaments and widening the ribbon until it reaches its final tapered shape. Geometry is grown, not installed. In short, tether geometry is the quiet heart of the elevator. Keep stress even, thicken where loads demand it, flatten where air will bite, split strength into many lanes, and make every joint graceful. Do that with a material worthy of the job, and the elevator stops looking impossible and starts looking like a long, disciplined piece of civil engineering, one that simply reaches higher than anything we have ever made. If the space elevator has a soul, it lives in the ribbon. Everything else, platforms, climbers, lasers, can be swapped or upgraded. The tether cannot be mediocre. It must be astonishing. The easiest way to see why is to talk about one number, specific strength. That is simply how strong a material is divided by how heavy it is. Think of it as strength per kilogram. A high specific strength means you can carry tension without dragging along too much of your own weight. Here is the core problem. A 36.0-kilometer ribbon must hold up not just the climber, it must hold up itself. Every meter below is tugging downward. Every meter above is tugging outward. If the material is too heavy for its strength, the ribbon will need to be so thick in the middle that it becomes impractical. Engineers encode this with a helpful yardstick called a characteristic length, how tall a hanging thread of that material could be before its bottom breaks under its own weight. For common metals, that length is only tens of kilometers. For high-end polymers and carbon fiber, it reaches a few hundred kilometers. For advanced carbon nanostructures in the lab, it stretches into the thousands of kilometers. A workable Earth elevator wants thousands, not hundreds. Put less technically, steel and aluminum are out on day one. Even Kevlar and ultra-high molecular weight polyethylene, famous for bulletproof vests and light ropes, struggle the moment you add healthy safety margins. Traditional composites are wonderful, but wonderful on planes is not enough for a sky-spanning ribbon. The elevator asks for a material family whose strength to weight is an order of magnitude better than aerospace carbon fiber, not just a small step better. Why talk about safety margins so early? Because the lab number for tensile strength is not the number the sky will see. Real materials have defects, micro cracks, voids, junctions where fibers meet, uneven coatings, and tiny bits of contamination. Over 36,000 kilometers, a tiny problem becomes a near certainty somewhere. Heat and cold make materials expand and contract. Ultraviolet light, oxygen, and atomic oxygen in the upper atmosphere attack polymers. Charged particles rough up surfaces. Micrometeoroids nick fibers. All of that eats into strength. Sensible engineering accepts this and builds in room. If a perfect strand might hold X, the operational ribbon should be sized as if it only holds a fraction of X, perhaps half, so it still has margin when nicked, heated, or aged. This is why engineers love redundancy. The ribbon is not a single bar. It is a highway made from many filaments running in parallel. If a pebble on that highway pops a tire, the car can change lanes. In materials terms, load redistributes around damage. But redundancy does not erase the demand for high specific strength. It just buys you time and graceful degradation. The baseline still has to be strong and light. So what would good enough look like in plain terms? Imagine a material that, strand for strand, is roughly 10 to 20 times better at strength per weight than steel, and comfortably above the best conventional composites. If you had that, the ribbon's thickest region near geostationary altitude could be only several times wider than the base, not hundreds of times. Manufacturing becomes plausible. Launch mass becomes manageable. Maintenance robots can actually replace segments in orbit. If you do not have that, the taper balloons into something you cannot build or afford. Carbon nanotubes and graphene are famous here because their tiny building blocks, individual tubes or sheets, are incredibly strong and light. In small samples, they hit record values. The leap we still wrestle with is scale. A single perfect nanotube measured in a microscope is one thing. A kilometer, class yarn made from trillions of them, with consistent bonding and almost no weak spots, is another. The same goes for graphene. A flawless atomic sheet looks invincible until you stitch billions together. Joints, voids, and mismatched grains become the real material. This is why process matters as much as chemistry. How do you spin, weave, and coat the filaments so each carries its fair share without cutting its neighbor? How do you inspect 36 0 kilometers for defects you cannot see with the eye? The ribbon needs built-in health. Fibers with conductive traces can broadcast their strain, temperature, and small breaks. Climber-borne scanners can map weak zones. Tiny repair bots can lay fresh filaments across scars. The material is not just a passive rope. It is a monitored and maintainable system. Temperature swings are another quiet killer. The lower ribbon crosses weather, hot days, cool nights, wet storms. Higher up, you get searing sunlight on one side and deep cold on the other as Earth turns. Different layers of the ribbon may expand by slightly different amounts. If expansions do not match, internal stresses creep in even before a climber touches the line. Designers counter with coatings that even out heating, with surface treatments that reflect some sunlight and radiate heat at night, and with active length control, reeling a tiny bit of tether in or out to keep overall tension inside the comfort zone. Creep the slow, permanent stretch. Some polymers suffer under constant load is a long-term concern. If your ribbon creeps, tension migrates to other fibers and stress concentrates. Materials with low creep or with molecular structures that resist long-term deformation are preferred. Again, carbon-based nanofibers look promising because their bonds are stiff, but promise must be proven in years-long tests, not weeks. Radiation and chemistry turn up at different altitudes. Atomic oxygen, abundant around 200-700 kilometers, erodes many polymers atom by atom. Protective coatings can slow that to a crawl. Farther up, ultraviolet and particle radiation darken and embrittle some materials. Stabilizers and topcoats help, but they add mass and must not undermine strength. The right recipe is a laminate, a load-bearing core protected by sacrificial skins you can renew. All of this loops back to the idea of design allowables, the strength values you are willing to use in calculations after you discount lab hype, manufacturing scatter, aging, and damage. A material that looks blazingly strong on a glossy chart may end up with a sober allowable only a little better than a good polymer once you take away the optimistic bits. The elevator only cares about those allowables. So when you hear, "We have a material strong enough for a space elevator," ask two simple follow-ups. First, how long was the sample and how many did you test? A single miracle fiber is not a ribbon. Second, what is the tested strength per weight after aging, humidity, temperature cycling, and radiation exposure? If those numbers stay high and consistent at scale, confidence grows. If they slide, the taper balloons and the project moves from hard to impossible. In short, the ribbon demands a rare combination: very high specific strength, reliable manufacturing at absurd length, resilience against heat, cold, oxygen, and radiation, and a structure that tolerates small wounds without catastrophic failure. The chemistry points toward advanced carbon. The engineering says, prove it at scale, monitor it non-stop, and keep healthy margins. Only then does the dream move from poetry to hardware. Let's put names to the dream fibers and keep the story practical. Carbon nanotubes are tiny cylinders of carbon. Graphene is a sheet, 1 atom thick. Diamond, like threads, are chains of carbon atoms locked into very stiff bonds. All three look like superheroes on paper because, atom for atom, they carry a lot of tension for very little weight. But a space elevator does not care about a perfect molecule. It cares about kilometers. The real job is to turn nanoscale bricks into long, repeatable yarns, and to weave those yarns into a ribbon that survives weather, vacuum, radiation, and years of traffic. Start with carbon nanotubes. Engineers have two main ways to make long CNT fibers. One grows dense forests of tubes on a wafer and draws them out like silk, twisting the bundle into a yarn as it leaves the surface. The other disperses short tubes in a liquid and spins them into a thread while they align and bind together. Both routes already produce useful fibers. Both still fall short of the dream numbers for three familiar reasons: alignment, cleanliness, and load transfer. If tubes tilt, some carry less force. If bits of catalyst or polymers sit between tubes, they behave like tiny cracks. And even if everything is clean and well aligned, the force still has to jump from tube to tube through the bonds that tie the bundle together. Weak junctions limit the strength long before a single perfect tube would break. Graphene fibers face a cousin problem. A small graphene sheet can be close to flawless, but long sheets must be stitched from many grains, and the seams become weak links. Makers stack, twist, and cross-link sheets to build round threads. The result can be strong and light, yet the eye-popping nanoscale values soften at the scale of kilometers. Still, graphene brings two gifts that help right away: excellent heat conduction and useful electrical conduction. Heat conduction wicks away hotspots near traction zones. Electrical conduction helps route static charge in the ionosphere and gives lightning a better path to ground, which matters near the base during storms. Diamond-like threads sound exotic, but they are simply carbon in a very rigid arrangement. Early samples are short. If chemists learn to grow them long and bundle them into fibers, their low creep and heat resistance could help in the lower atmosphere, where warm air and sunlight squeeze safety margins. For now, they are a research path, not a product line. So what does a buildable ribbon look like with realistic materials? Think in layers. At the center sits a load-bearing core made of the strongest fibers. Factories can ship that year. Nanotube bundles first, graphene-reinforced yarns as they mature, and diamond-like strands later if they arrive. Around that core are sacrificial skins that the climber grips. Those skins protect the core from wear and can be swapped out regularly. Woven into the outer layers are thin conductive paths to manage static and give lightning a controlled route. Thin protective coats guard against ultraviolet light, atomic oxygen, and moisture. Between structural lanes run hair-thin sensor fibers that read strain, temperature, and small breaks so operators can see problems before they grow. Redundancy belongs in the weave, instead of one solid strap. The ribbon is many parallel lanes tied by cross members, the ladder, or tether style. If a micrometeoroid slices a lane, the cross members bridge the gap and pass load to neighbors. Small repair robots ride to the wound, bond in fresh filaments, and restore capacity while traffic slows but continues. Over time, the outer skins are replaced on a schedule, like tires. The inner core lives longer and is touched only when health monitors ask for it. Joints are unavoidable, so make them gentle. No one ships a 36, 0-kilometer spool. The ribbon is a chain of modules with long, tapered overlaps so load transfers gradually and no single stitch feels the entire force. Bonding can mix microhooks, nanoscale welding at contact points, and tough polymer bridges. Every joint must be inspectable by a passing climber and replaceable without shutting the line down. Heat is a quiet enemy. Traction, tiny slips, and routed power create warmth right where strength matters most. Protective skins and conductive threads should wick heat sideways to the climber's radiators. Materials that keep their strength when warm earn a premium. Many polymers soften just when the sun and air are unkind near the base. Graphene's thermal conductivity helps. So do thin metallic meshes in the outer layers, as long as they do not add too much mass. Cost and scale sound daunting, thousands of tons over decades, but we have seen this story with solar panels, LEDs, and batteries. Learning curves push cost down and quality up. The elevator should start with a thin seed ribbon that lifts small payloads. Each ascent carries new filament and fresh skins. Capacity grows in seasons, not decades, and price per kilogram falls as factories learn. Testing turns optimism into trust. On the ground, kilometer reels can hold fibers at constant load for months, while chambers bake, freeze, and bathe them in ultraviolet light. Atomic oxygen rigs replicate the erosive layer of the upper atmosphere. Ion sources simulate the ionosphere. In the stratosphere, long balloon flights expose samples to cold, dryness, and real sunlight for weeks. In orbit, Pathfinder missions fly ribbon segments and log health as micrometeoroids and vacuum do their work. Those data feed back into design allowables, the sober numbers engineers actually use. Time is the other test. Creep the slow stretch under constant load and fatigue. The damage from many small cycles silently eat margin. The answer is strict but simple. Choose chemistries with low creep, operate well below any limit, and replace modules before they age out. Treat the ribbon like a railroad. Rails are swapped on a schedule long before they crack. Practical design accepts imperfection. The goal is not a flawless super rope. It is a forgiving network whose weak patches are found early and fixed quickly. That is why monitoring matters as much as peak strength. If a module's health score trends down, operations plan a swap rather than argue. Spare modules wait in orbit. Climbers carry toolkits and fresh filament. Downtime is measured in hours, not seasons. Could hybrids help while carbon matures? Yes. Early ribbons may blend today's best polymers with carbon lanes, gaining redundancy and lowering cost. As CNT and graphene plants improve, operators phase in stronger modules. The geometry stays the same. The allowable stresses rise year by year, shrinking the taper and boosting throughput. Bottom line, we do not need a miracle fiber that never breaks. We need fibers that are strong for their weight. Factories that make them by the kilometer with steady quality, coatings that protect them from air and light, and a maintenance culture that treats the tether as living infrastructure. Carbon nanostructures remain the frontrunners because their bonds deliver the strength to weight the physics demands. With that system in hand, the material question becomes a slope we can climb steep, but not vertical. Architecture turns strong fibers into a dependable elevator. In plain terms, choose a shape that behaves in air and space, divide strength so damage stays local, give climbers a durable surface, and make every kilometer buildable and replaceable without shutting down. Shape first. A flat ribbon beats around cable. It slices wind, resists vortex shedding, and gives climbers a broad grip. Picture a long ladder, very thin through thickness, much wider across, with a gentle twist. In bad weather, the lowest stretch can wear a slim storm sleeve, an aerodynamic shroud with lightning receptors. Above the jet streams, it flies bare. Strength lives in a mesh, not a monolith. Instead of one strap, the tether is many parallel lanes tied by cross members, a ladder, like tether. If a micrometeoroid cuts one lane, the rungs shift load to neighbors, and the injury stays local. The pattern also makes repairs practical, while traffic only slows. The mesh follows the taper. Near geostationary altitude, where tension peaks, the ribbon has more lanes and thicker core. Where loads ease, it slims. Transitions are smooth, so stress does not pile up. Think of a highway that gains lanes in the city and merges in the countryside. Where surfaces are separate from strength, climbers use traction wheels, clamps, or induction pads, and that contact scuffs and heats. The outer plies are sacrificial tread strips for grip and heat spreading. They are swapped often. Beneath them sits the structural core, carbon fiber bundles laid in lanes. Between lanes run hair-thin sensor fibers for strain and temperature. Thin conductive traces in non-structural plies manage static, guide lightning near the base, and power small sensors. Power from motion does not flow through the tether. It would be too heavy. Energy comes from beamed power, laser or microwave, and from solar once above weather. The tether's conductors are for housekeeping only. Communication can ride on optical fiber woven into non-structural plies or on radio. Modularity makes the tether real. The ribbon is built from many modules, each tens to hundreds of kilometers long, joined by long, tapered overlaps. Overlaps transfer load gradually so no single stitch is critical. Splices have several parallel paths, giving time to swap a tired sub-connection. Joints include inspection marks, so passing climbers can verify alignment and load. Way stations are simple, widened sections with anchor points, spare filament cassettes, and docks for maintenance spots. One just above the atmosphere handles the storm sleeve and lightning brushes. A low-orbit node stores spare modules and tools. Near geostationary orbit, the main hub hosts spools of replacement ribbon, traffic control computers, and small thrusters for fine control. The anchor sits on a mobile ocean platform at the equator. Capstans reel in or out a little tether to keep tension inside a safe band as temperature and traffic change. Lightning towers and surge arresters give storms a preferred target. The platform can steam to dodge cyclones and stay under the line as winds nudge it. At the top, the counterweight interface is a compact hub with several arms to ballast masses or a captured rock, and pods with efficient electric thrusters. Multiple arms spread control forces. If momentum needs rebalancing after heavy ascents, the hub can reel a little tether in or out or shift ballast along an arm. Stability hardware rides along. Tune dampers, small masses on short sliders, live where models predict strong oscillations. When the ribbon starts a specific sway, the dampers move out of phase and absorb energy, as in tall buildings. At the base, winches tug with tiny phase shifts to bleed waves. At the top, trim thrusters nudge the line back to center. Traffic stays smooth by schedule. Only as many climbers are on the line as the ribbon can handle without exciting large waves, and departures are timed so momentum trades cancel. For flexibility, short passing bays at a few altitudes outside the most stressed region let a slow vehicle wait while a faster one goes by. Protection changes with altitude. In the first 50 kilometers, the storm sleeve adds drag control and a guided path for lightning. The ionospheric stretch gets coatings that resist charged oxygen and ultraviolet. In space, thin replaceable bump layers help against sand grain impacts. Above low orbit, debris tracking informs short traffic holds or tiny yaw maneuvers during predicted conjunctions. Emergency features are baked in. The base has a quick-release coupling, so the tether can be detached in a rare severe event. The lower segment then falls into a pre-cleared ocean zone, while the upper system climbs slightly in orbit under the pull of the counterweight and waits for reconnection. Midline fuses are avoided, but modules are designed to fail gently if grossly overloaded, peeling rather than snapping. Growth uses the same blueprint at small scale. We start with a thin seed ribbon, just enough to hold itself and carry tiny climbers. Each ascent adds lanes and fresh skins. Capacity rises step by step until the full tapered mesh is in place. The geometry does not change, it thickens. This grow the highway while using it approach ties cost to progress and spreads risk over time. Awareness makes it sustainable. Every module reports strain, temperature, and small breaks. Way stations merge the data into a live health map from sea to counterweight. When a region's score drifts, maintenance is scheduled. A climber docks, unzips the old overlap, zips the new one, checks load transfer, and sends the worn module for recycling. The elevator keeps running. In one sentence, tether architecture turns extreme fibers into reliable infrastructure. A flat, tapered mesh of many lanes, sacrificial skins for grip and weather, modular segments with gentle splices, small way stations, smart damping, and clear plans for growth and emergencies. With that blueprint, the space elevator stops being a fragile rope and becomes a system with room for error and a path to routine use. A space elevator stands because it is balanced, not because it is rigid. Picture a baton spun between two fingers. Spin keeps it straight. Only if the baton's sweet spot, the center of mass, sits in the right place. For the elevator, that sweet spot is the geostationary ring. Everything below that ring is pulled inward by gravity. Everything above is pulled outward by Earth's rotation. The counterweight's job is to make those two pulls add up to steady, healthy tension all along the ribbon. There are two clean ways to get that balance. One is leverage. Extend the tether far above geostationary orbit, so the long tail itself supplies outward pull. The other is ballast. Attach deliberate mass at the far end. In practice, you mix both. A long tail multiplies every kilogram you put high, so you don't need a ridiculous lump of mass. Modest, movable ballast then lets operators fine-tune the balance day to day. Why start with length? Far above the ring, the outward centrifugal effect is stronger. A kilogram at very high altitude supplies more outward tug than the same kilogram near geostationary orbit. That leverage stiffens the whole system, keeps the lower ribbon from slackening in rough weather, and gives a bonus. Release a payload from high on the tail, and it leaves with extra energy, reaching higher orbits or even escape without much propellant. Length turns the elevator into both a ladder and a slingshot. Ballast still earns its keep. The tip can host a compact hub with masses that slide on short arms, like a dumbbell you can adjust. Slide them inward or outward, and you nudge the whole system's center of mass while the ribbon stays where it is. If a week of heavy upward traffic has leaned the line a little west, operators shift ballast or reel a bit of tether in or out to recenter the elevator over its assigned longitude. What is the ballast made of? Early on, whatever is cheap to loft, spent upper stages, empty propellant tanks, and purpose-built plates and trusses. Later, space tugs can deliver rock or metal from near-Earth asteroids or from the Moon, so you're not paying Earth launch prices for dumb mass. In all cases, the counterweight should be a tidy, well-built package with attachment points for reels, thrusters, solar arrays, and sensors, not a loose pile that might shed debris. A captured asteroid sounds romantic, but it adds risk. Natural bodies are irregular and can shed fragments. They complicate flight rules and planetary protection concerns. If one is ever used, it should be small, well-characterized, and wrapped in containment. The practical path is manufactured ballast, you understand, down to the bolt. Momentum bookkeeping is the counterweight's daily chore. A climber that rises must gain sideways speed to keep pace with Earth at higher altitude. That speed is borrowed from the system. The line leans a little, and the upper hub loses a touch of orbital energy. A loaded climber that descends pays some of that back. A payload released high above the ring takes energy with it. You schedule traffic so these trades mostly cancel, pair an ascent with a descent, or time a high-altitude release after a heavy downbound delivery. Small leftovers are handled by tiny thruster burns and slow reeling. Reeling is a quiet superpower. Both the base and the top have reels. Add a few meters of length, or take a few away, and you shift tension and nudge the center of mass. Slow, coordinated reeling while a climber is on the line keeps stress inside a narrow band and prevents big waves from growing. Over months, tiny reeling moves also absorb small changes in Earth's rotation, keeping the sweet spot pinned to the geostationary ring without wasting propellant. How big is big enough for the counterweight? There is no magic number. The right size is the one that gives comfortable tension at the base in rough weather, stable margins while several climbers are on the ribbon, and enough control authority for station keeping. Too small, and the lower ribbon can go slack during a storm or an unlucky traffic pattern. Too large, and you pay for mass you don't need and for bigger thrusters to steer it. Most designs favor more length and modest ballast instead of brute weight. The counterweight hub doubles as a quiet spaceport. It hosts docks for maintenance craft, spools of spare ribbon, and a small crane for swapping modules near the tip where loads are lighter. Its thrusters are high-efficiency electric types, Hall or Ion class, chosen for long life, not brute force. They point tangentially to adjust longitude and radially to trim tension. Broad solar wings power them and feed communications and sensors. Safety threads through everything. If the base ever has to quick release, say, to avoid a truly extreme storm, the upper system must fly safely on its own. With the ground end gone, the counterweight pulls the remaining ribbon outward into a slightly higher, safe orbit, where it can wait while crews prepare reconnection. During that period, the hub's job is to keep the system tidy, control spin, avoid nearby satellites, and orient the stowed lower end so recovery craft can reach it cleanly. Debris avoidance is part of that tidy life. The ribbon can't easily dodge fast junk, but the top can yaw by a fraction of a degree with modest fuel, shifting the line's longitude by tens of kilometers for a short time. That small sidestep, timed with tracking data, lets most conjunctions pass. Afterward, the hub eases the system back to center. Thermal and electrical realities reach the tip too. The hub bakes in full sun and freezes in shadow. Its structure must absorb daily swings without twisting the ribbon mount. Its power electronics must ride through plasma weather without surges. Lightning never reaches this high, but static charge and auroral currents can. Conductive paths down the ribbon and robust grounding at the base give that charge a safe exit to the ocean platform. Growth strategy leans on the counterweight. We begin with a thin seed ribbon and a modest hub, just enough ballast to hold tension. Each early ascent carries new filament for the ribbon and fresh plates or tanks for the hub. Capacity rises in lockstep. When the tail is long enough, the hub can host a small logistics port, a parking place for tugs, and a warehouse for spares, keeping maintenance away from the crowded geostationary belt. One more benefit of leverage: it gives operators time. A long tail with modest ballast reacts slowly to small pushes, so control inputs can be gentle. That helps during climber transits, weather holds, and minor slips in the schedule. The goal is never a perfectly rigid line. The goal is a system that refuses to amplify trouble. In the end, the counterweight is the elevator's attitude. Choose leverage over brute mass, add movable ballast, keep reels and thrusters ready, and the ribbon below can be lighter, the base calmer, and the climb more routine. Balance is not a part you buy, it is a posture you maintain every day, and the counterweight is the hand that holds that posture steady. No one builds a 36 0-kilometer ribbon from the ground up. You build it from geostationary orbit down and up at the same time. Think of it like fishing from the sky. A spacecraft at geostationary altitude pays out a thin seed ribbon toward Earth, while also paying out a tail upward toward a counterweight. By growing both directions together, the center of mass stays near the geostationary ring, and tension stays healthy. Step 0 is staging the hub. Multiple launches deliver modules, power, reels, guidance, spares to a worksite near geostationary orbit. Electric tugs do the final push to the exact slot over the equator. Technicians on small robotic craft bolt everything to a compact truss. The truss holds two great spools, one aimed down to Earth, one aimed up to the future counterweight. The base station at sea is already waiting under the longitude, on a mobile platform with tall lightning masts, big capstans, and a clear safety zone. Now the spool down begins. The seed ribbon is hair-thin compared to the final tether. It is strong enough to hold itself and a tiny climber, nothing more. Operators release it at a walking pace meters per second. Not 10, so waves do not build, and so guidance can react. Every few kilometers, small sensor tags ride the ribbon. They report strain, twist, and charge. The down spool is smooth, continuous, and boring on purpose. Passing through low Earth orbit is the riskiest part of the descent. Debris is common there. The seed ribbon is so thin that most small junk would pass without cutting it, but operators do not rely on luck. They choose a time when the track debris field is calm. The top hub can yaw a fraction of a degree to slide the line's longitude a few tens of kilometers for a day, then return to center after the heaviest traffic passes. The descent timeline includes scheduled holds to let predicted conjunctions cross harmlessly. Atmosphere brings new problems and new tools as the tip dips under about 100 kilometers. Drag and heat matter. A small, blunt capture capsule rides the end. Think of a mini re-entry body with a drogue chute and a radio beacon. It shields the tip, slows it down, and gives the base team something easy to see on radar. Below about 30 kilometers, the capsule deploys a long, high-visibility streamer. Airspace is closed along the track. Weather teams watch winds in layers. If a storm brews, operators pause the descent and wait. The last few kilometers are choreography. A helicopter or high-altitude balloon can snag a trailing line from the capsule and hand it to a ship. Or the capsule can splash down in a pre-cleared patch of ocean inside reach of the platform's cranes. Either way, the base crew couples the seed ribbon to the platform's capstan through a quick-release device. The device is the seatbelt. If the first night brings a freak storm, operators can detach, let the lower few hundred kilometers fall into the empty zone, and try again later without risking the whole line. While all of that happens below, the hub is also spooling upward. A light tail tens of thousands of kilometers long unwinds into space, carrying small ballast masses and later docking with the counterweight hub. Electric thrusters hold the hub on station as torques shift. By the time the seed ribbon meets the sea platform, the upward tail is long enough that the whole system has comfortable tension and a calm personality. Leverage beats brute mass here. Once the seed is anchored, the elevator is born, but it is not strong. The first climbers are feather-light machines whose only job is to lay more tether. Each carries spools of filament, climbs a few hundred kilometers, bonds new lanes beside the seed, and returns. The next climber starts higher, adds more, and so on. Think of striping a highway while cars still drive. With each round trip, the ribbon gets wider, the mesh grows, and the safe load rises. Growth is paced by data. The seed sensor tags now feed a live health map from sea level to space. Strain spikes hint at twist or local damage. Temperature peaks spot hot zones where coatings need help. Operators adjust climb speed, pause for a day-night cycle to settle waves, then resume. Early on, only one climber is on the ribbon. Later, two pass at agreed waypoints when the mesh is strong. Schedules always avoid exciting resonances. You do not drum on your own guitar string. The lower 50 kilometers get special treatment. A slim storm sleeve slides up and down this section like a sock. It smooths winds, adds lightning receptors, and houses replaceable sacrificial skins for the climber's traction. During calm seasons, the sleeve parks at the base to reduce drag. During storm seasons, it rides higher. Maintenance crews can swap damaged panels without touching the structural core. Power and comms are bootstrapped as well. The first climbers use batteries and small solar wings, once above weather. As capacity grows, ground lasers or microwave beams feed power to their receivers, and the climbers' radiators dump heat to the sky. Optical fiber woven into non-structural plies gives the ribbon a private data backbone. The base, hub, and way stations chat without relying on crowded radio bands. The counterweight hub becomes the quiet conductor of this symphony. Its thrusters trim longitude and tension. Its reels add or remove a few meters a day to keep the center of mass on the geostationary ring as the ribbon's mass grows. Its arms slide ballast weights a little in or out to cancel the momentum trades from each ascent. Nothing is dramatic. Everything is slow, deliberate, and measured. Risk never goes to zero. A small meteoroid may nick a lane. The health map shows a new bruise. Operators slow traffic. A repair climber goes up with a fresh module, splices it in, and brings the damaged piece down for study. Sometimes the answer is as simple as changing a coating recipe. Sometimes it means adding more cross members in a certain altitude band. The design evolves while the system stays alive. Regulatory life runs in parallel. Maritime and aviation corridors under the ribbon get routine closures during key operations. The platform publishes schedules like a spaceport at sea. Emergency services rehearse detaching the base and clearing the zone. Insurance and liability frameworks mature along with the hardware. None of it is glamorous, all of it is necessary. Commissioning ends not with a ribbon cutting, but with a first real haul. A cargo climber carries a small satellite bus to the hub. It disconnects, and the hub releases it to a nearby slot. The same climber returns with old spares and samples for ground labs. After a few such sorties, price per kilogram falls, traffic plans get bolder, and the elevator moves from experiment to infrastructure. From a listener's seat, the lesson is simple. We do not leap to a full-strength elevator. We grow it like a living bridge. Seed from the sky, capture at sea, widen by climbing, and strengthen by steady routine. The physics demands patience and rhythm. Honor that rhythm, and a ribbon you can barely see on day one becomes a highway to space one season at a time. If the tether is the highway, the climber is the truck. Its job sounds simple: go up, come down, carry payload, but the details decide whether the elevator feels routine or risky. A good climber grips without chewing the ribbon, guides itself without drama, dumps heat without frying parts, and obeys traffic rules so waves never build on the line. Start with the grip. Most designs use traction wheels that pinch the ribbon between opposing rollers. The contact pressure is high but carefully controlled, so the wheels don't slip in rain, frost, or thin air. The wheels run on sacrificial outer plies. The tread layers, so the strength carrying core is never scuffed. Some concepts add clamp bars that close gently during emergencies. Others include small magnetic pads that add a touch of force in service zones where the ribbon has conductive strips. The rule is constant. Traction is strong, predictable, and kind to the ribbon. Twist is the silent enemy of grip. If a single motor tries to drive from one side, it can torque the ribbon. To cancel that, the climber uses symmetric drives mirrored wheel trains on both faces, so the net twist is near zero. A light frame links the drives without flexing. When the climber crosses a joint between ribbon modules, its wheels widen their stance by a few millimeters and ride the long, tapered overlap as if it were a shallow speed bump. Guidance is simple in air, precise in space. In the lowest tens of kilometers, cameras and LiDAR lock onto printed fiducials on the ribbon skins. Above the clouds, star trackers and horizon sensors add absolute attitude. Tiny side thrusters or trim wheels keep the cabin centered. The ribbon itself carries a thin optical fiber for data. The climber chats with the base, with way stations, and with the counterweight hub in a steady, low-latency stream. If sensors disagree, the autopilot slows and asks for help rather than guess. Power is beamed. We'll unpack the beam in the next section. For the climber's perspective, think of it this way. On the pad, it uses batteries. In the first slice of sky, it sips beam power through a receiver. And once above weather, it adds solar panels on fold-out wings. The power chain feeds high-efficiency electric motors and a cooling system. The motors are quiet and geared for steady pull, not sprinting. When the beam blinks for a second clouds, gust, or a quick safety, cut the batteries, bridge the gap so the drive never jerks. Heat is where many paper designs fail. Motors, electronics, and traction make heat exactly where strength matters, at the contact zone. In air, you can dump some heat to moving air. In space, you cannot. That is why the climber carries radiators, thin panels that glow heat away as infrared. During the first hour, radiators are partially stowed to cut drag. Once above the thick air, they swing wide. A liquid loop ferries heat from motors and the contact shoes to the panels. If a big descent is planned, the climber uses regenerative braking to turn motion back into electricity. If the beam system can't absorb the return, the climber burns the excess in resistors and spreads the heat across its panels. Speed is chosen to be boring. Faster is tempting, but high speed launches bigger waves in the ribbon and spikes heating at the grip. Early operations will run at conservative speeds, think tens to a few hundreds of kilometers per hour. So a full ascent takes many hours, not minutes. That sounds slow. It is safe. As the ribbon thickens and damping improves, speeds rise within the limits set by wave control and heat. Payload handling should be gentle and predictable. Cargo rides in a pressurized or sealed bay with shock mounts. The center of mass sits close to the ribbon, so the climber does not lean, hatches face away from the ribbon to keep debris out of the mesh. For human flights later on, the cabin adds life support, a quiet interior, and redundant restraints. But people come after years of cargo, only experience. Rules of the road keep the ribbon calm. Departures are scheduled so momentum trades cancel. A heavy upbound leaves near the time a heavy downbound passes the stress peak, and their tugs offset. Passing happens at planned bays, widened sections outside the most stressed region. Right-of-way is clear. Emergency traffic first, then downbound, which returns momentum to the system, then upbound. Speed caps apply near joints, way stations, and the ionosphere, where charging is a risk. Weather discipline is strict. Lightning forecasts, wind profiles, and storm tracks gate departures. If a cell blossoms along the track, the base holds the next launch or recalls an early ascent to a low parking altitude under the storm sleeve. The climber's skins and the ribbon's conductive paths give lightning a preferred route. But the best strike is the one you never invite. Charging in the ionosphere is addressed by bonding. The climber ties all metal parts, radiators, and receivers to a common ground linked to the ribbon's conductive traces. That way, any charge that builds bleeds away without arcing. The cabin avoids sharp points. Edges are rounded so electric fields stay low. Braking and fail-safe hold are last lines, not daily tools. If beam power hard fails, the climber automatically clamps with a friction brake that squeezes on sacrificial pads, not on the structural core, and holds position. A slim emergency battery keeps avionics and lights on. If the failure occurs below a service bay, ground reels may slowly lower the climber by easing ribbon length a hair while the brake modulates. Above the bays, a rescue car can climb up from below and tow. The point is to park, think, and act slowly, not to fall. Maintenance rides with routine traffic. Some climbers are groomers rather than haulers. They scan the ribbon with high-resolution cameras and eddy current probes, replace worn skins, and carry fresh filament to stitch over small wounds. They are the elevator's street sweepers and road crews. Their schedules are steady and dull, which is exactly what you want for safety. Noise and vibration matter for longevity. The drivetrains use balanced rollers and low-ripple power electronics, so the grip never chatters. Any periodic motion is poison because it can pump a resonance on the ribbon. The autopilot changes speed by a few % off any known natural frequency of the line, the way you change step to stop a swaying bridge. Mass is a tax. Every extra kilogram costs energy and heat. Frames are minimal trusses. Panels are thin. Interiors are function first. Toolkits for groomers are modular, so they carry only what that mission needs. Even paint has a job. Optical properties are tuned, so the craft stays thermally stable under sun and shade. Descent is not an afterthought. Coming down safely returns momentum to the system and recovers energy in regenerative mode if the power chain allows. Downbound traffic also brings broken modules to ground labs, where coatings, bonds, and fibers are autopsied to improve recipes. The elevator gets better one descent at a time. In short, a climber is not a rocket on a rope. It is a steady machine that trades speed for reliability, treats the ribbon with respect, and follows simple rules so the whole system stays quiet. Grip cleanly, guide calmly, dump heat well, and never excite waves. Do those 4 things, and every trip feels the same, which is another way of saying the elevator has grown up. Rockets carry their power as propellant. A climber does not. Most of its energy arrives from the ground or from orbit as a beam. That choice keeps the vehicle light, but it moves all the hard work into optics, antennas, tracking, and heat management. Done well, beamed power makes the elevator feel steady and electric. Done poorly, it makes the ride hot and twitchy. Let's keep it simple and practical. There are 2 main ways to beam power: laser light and microwaves. Lasers use light you cannot see or barely can near infrared wavelengths that pass through air reasonably well. A laser receiver on the climber is basically a tailored solar panel. It turns light into electricity. Microwaves use radio waves, the kind your kitchen oven and Wi-Fi live near. A climber's rectenna, a mesh of tiny antennas with diodes, turns the radio energy into DC power. Lasers are compact and focused tightly. A ground station can paint a small bright spot on the receiver, even hundreds of kilometers up, if the air is clear. That means a smaller, lighter receiver on the climber and less extra heating of the air around the beam. The trade-off is weather. Clouds scatter light. Heavy haze and rain can block it completely. To fight that, laser stations sit in dry places, often at sea near the equator where they can sail to clearer skies, or on mountain slopes above the worst clouds. Adaptive optics, deformable mirrors that wiggle to cancel atmospheric blur, help keep the spot sharp as the climber rises. Microwaves punch through clouds and fog better. A rainy day that kills a laser may still allow a microwave link. Rectennas also convert with high efficiency and shed less waste heat in the receiver. The cost is size. Microwaves spread more as they travel, so the ground antenna must be big think fields, not rooftops, and the climber's rectenna must be broad to catch a useful share. That adds drag in air unless the rectenna folds or rides as a thin, see-through mesh aligned with the wind. Either way, power levels are serious but not wild. Climbing thousands of kilometers takes energy measured in tens of megajoules per kilogram, delivered over many hours. A cargo climber might need a steady electrical feed of a few megawatts to low tens of megawatts depending on mass and speed. That power lands on a receiver that must keep itself cool. In air, a little cooling comes from the breeze. Above the atmosphere, radiators do all the work. The climbers heat loop ferries warmth from motors and receivers out to thin panels that glow in infrared. Early operations limit speed so the radiator area stays sane. Pointing and tracking make the beam usable. The ground station locks onto a bright target marker on the climber, an LED pattern for lasers, a transponder for microwaves. The computer knows the ribbon's shape and the climber's plan. It aims slightly ahead, so the beam lands where the climber will be a fraction of a second later. If the beam jitters, the receiver's power electronics smooth the bumps with short-term batteries, so the motors never see a hiccup. If tracking is lost, or a bird or aircraft strays into a protected zone, the beam snaps off in milliseconds. Safety interlocks are not optional. They are part of the license to operate. You do not want a single point of failure, so power comes from more than one place. Ground-up laser or microwave is the primary feed through the weather layer. Above the clouds, the climber spreads small solar wings for extra margin. Near and above geostationary altitude, a second station on the counterweight hub can beam down along the tether's line of sight, bypassing the atmosphere entirely. The two sources hand off gently, overlapping for minutes so the batteries barely notice. If both beams blink, the climber can pause on its friction brakes, powered by its emergency pack, and wait for the link to resume. What wavelengths work best? For lasers, bands near the atmospheric windows are popular. Fiber laser lines that are safer for eyes and work well in air pair with dedicated photovoltaic cells tuned to that color. Those cells can reach high conversion efficiency when matched to a single laser line. For microwaves, industrial science bands with mature hardware and good rectenna performance are common. Engineers pick exact frequencies by balancing conversion efficiency, antenna size, and the local radio environment. Efficiency matters because every percent you lose becomes heat. If your laser chain on the ground is, say, half efficient from wall plug to beam, and your receiver is a bit less than that from light to electricity, the product sets how much waste heat both ends must dump. Big chillers and cooling ponds live at the ground site. Broad radiators ride on the climber. Microwaves often win on total end-to-end efficiency, but their larger antennas and rectennas complicate the lower altitude portion of the climb. There is no free lunch, only different kitchens. Air itself reacts to strong beams. For lasers, water vapor and aerosols scatter some light and add random twinkle. Adaptive optics and multiple smaller beams summed at the climber reduce hotspots and improve reliability. For microwaves, air heating is tiny, but regulatory rules about power density and side lobes energy off to the sides are strict. Phased arrays, which steer radio beams electronically, keep energy where it belongs and notch out forbidden directions. Safety is as much procedure as hardware. The C platform declares a no-fly cylinder aligned with the ribbon whenever the beam is on. Aircraft and drones avoid it the way they avoid a rocket launch corridor. Maritime notices do the same for ships. The ribbon's lowest section can host a beam catcher, a dull absorber panel that soaks stray energy during tests. Lightning systems on the platform stand ready. During a storm window, the platform simply does not beam. Grid power feeds the ground station. On a calm day, it feels like a small factory. Megawatts in, cooling water humming, control room quiet. On the ocean, the platform can carry gas turbines and battery farms as backup. The beam only runs when weather, airspace, and ribbon health are all green. That discipline turns a wild-sounding idea into a routine shift. Operators care more about checklists than heroics. How do you start before the big stations exist? Early climbers fly on batteries plus small ground lasers, taking advantage of slow speeds and long nights. Each trip hauls up parts of the permanent beam system, better receivers, bigger radiators, smarter power electronics, so the next descent can move faster or carry more. Capacity grows with the infrastructure. The elevator is built by the elevator. Heat at the grip zone gets special attention. Traction makes micro-slips. Micro-slips make heat. The tread skins under the wheels are high-conductivity layers that spread warmth quickly to coolant lines. Motor controllers ramp torque smoothly to avoid spikes. During downbound runs, regenerative braking turns motion back into electricity. If the beam system can absorb it, energy flows down the line and lowers the ground draw. If not, the climber sends the excess to resistor banks bolted to radiators and simply glows it away. Could we someday feed power through the tether itself? The main structural lanes stay purely mechanical to protect strength to weight. But non-structural conductors already ride along for sensors and static control. In the far future, a separate, lightweight power line could hang alongside in sections swappable and sacrificial, so way stations can host local tools and emergency chargers. For now, beamed energy is simpler and safer. In one sentence, pick a beam that fits your weather, build conservative receivers with lots of cooling, point steadily, shut off quickly when anything looks wrong, and let overlapping sources hand off the load so the motors never feel a hiccup. Power is not a stunt, it is a rhythm. Keep the rhythm, and the elevator climbs like a quiet electric train into a black sky. A space elevator would cross every kind of sky. It begins in humid air with storms and birds, passes through thin, cold blue where jets cruise, skims the edge of space, then spends most of its life in vacuum, lit by the sun. Making that trip feel routine means understanding each layer and using simple, repeatable habits that keep the system quiet. Weather comes first. The base lives on a mobile ocean platform on the equator, so it can move under calmer skies and dodge cyclones. The lowest section of tether wears a slim storm sleeve, an aerodynamic shroud with lightning receptors and smooth panels that let wind slip by. When forecasts worsen, departures wait. The safest tool is a schedule that respects weather. Rain and icing are short, predictable issues. Hydrophobic coatings make water bead and run. Rounded edges deny ice a foothold. If frost threatens, climbs pause. This is airline discipline applied to a taller route. A few tens of kilometers up, winds smooth out while cold intensifies. The climber keeps radiators partly stowed until drag falls, then spreads them wide. From here on, heat moves by radiation, not by breeze. The tether's outer skins reflect sunlight and resist ultraviolet. The structural core sits beneath those skins to avoid harsh day-night swings. Near the common Kármán line, drag becomes a whisper. New risks replace old ones. In low orbit, micrometeoroids and small debris arrive at several kilometers per second. You cannot armor a 36-0-kilometer line, so you make it forgiving. The tether is a mesh of many lanes tied with crossmembers, not a solid strap. If one lane is nicked, rungs pass load around the wound. Small repair robots stitch fresh filaments over the bruise. Tracking data guides, short traffic holds, or tiny yaw maneuvers at the top so predicted conjunctions pass by. Atomic oxygen prowls the same altitudes. It erodes many polymers one molecule at a time. The tether's outer skins carry sacrificial coatings tuned for that chemistry. When those skins age, groomer climbers swap panels. The core fibers remain protected. Higher up, the air becomes plasma. The ionosphere, charged particles and currents change with day, night, and solar weather. Metal can charge to high voltage and arc when it meets a different potential. The cure is bonding and a gentle bleed. Conductive paths run along the tether. The climber ties all metal to a common ground linked to those paths. Charge trickles away instead of jumping as a spark. Sharp points are avoided, so electric fields stay low, and radios and receivers are built with generous margin. Beyond low orbit, the ride enters the radiation belt's donuts of trapped particles shaped by Earth's magnetic field. The inner belt sits a few thousand kilometers up. The outer belt spans tens of thousands. Geostationary orbit lies within the outer belt, so the elevator lives with it for life. For the tether, radiation slowly ages coatings and sensors. For electronics, it adds noise and dose. Shielding is targeted, not heavy. Avionics sit in compact vaults. Memories use error, correcting code. And critical circuits can be power, cycled or rerouted during high activity. Solar storms are the wild cards. When the sun throws a tantrum, particle flux rises, the ionosphere roils, and the belts puff. The elevator responds like an airline in a blizzard. Slow or pause. A space weather desk watches trusted forecasts and the system's own sensors. If thresholds are crossed, new departures wait, and vehicles already in the belts hold at safe parking altitudes. The tether itself is fine, it is passive structure, but electronics and beamed power links prefer calm skies. Thermal life becomes the daily beat in space. Sunlit faces get hot, shaded faces get cold. The tether breathes as layers expand and contract. Sensors watch length and strain. Capstans at the base and reels at the counterweight add or remove a few meters over a day to hold tension steady. The goal is not zero motion. The goal is small, slow motion that never piles into fatigue. Equatorial skies avoid the brightest auroras, but equatorial plasma still has moods, nighttime bubbles, and drifts. Operators time sensitive measurements and beam handoffs away from the worst periods. Good bonding keeps small surges from spiking. Closer to the ground, biology matters. Birds, salt spray, and insects can foul gear. The platform keeps the base tidy and covers equipment when beams are off. Sleeve panels are smooth and easy to clean. If seabirds adopt the lightning mast, crews add gentle deterrents so wildlife stays safe and hardware stays clean. Noise and vibration travel with the environment. Gusts and day-night heating launch waves in the tether, tuned mass dampers, and smart winch tugs at the base bleed those waves away. The aim is a line that sways like a calm bridge, not a jump rope. Climbers help by avoiding steady beats that match natural frequencies. A little randomness in speed is a feature, not a bug. Finally, law and habit connect to the environment. Airspace and sea lanes under the tether become routine launch corridors. Notices go out before a beam lights. Fishing boats and hobby drones stay clear during operations. The platform publishes a daily rhythm the public can count on. When weather is green, climbs go. When the sun or storms say, "Not today," the schedule slides. Reliability grows from that honesty. In one sweep, storms and lightning at the bottom, thin cold air above, debris and atomic oxygen in low orbit, charging in the ionosphere, radiation belts around geostationary altitude, and quiet vacuum beyond all, met with coatings, scheduling, grounding, light shielding, tracking, and patience. The elevator does not conquer its environment. It collaborates with it, the way good ships work with the sea. An elevator is useful only if it moves real mass every day, on time, at a predictable price. Throughput has 3 knobs: climber speed, spacing, headway, and payload per vehicle. Economics adds 2 more: electricity for the climb and the cost of keeping the system healthy. Speed rewards patience. Higher speed pumps bigger waves into the tether and heats the grip. Early runs stay around 100–200 kilometers per hour. At 150 kilometers, A ride to geostationary altitude takes roughly 10 days. It sounds slow until you remember the highway model. Many vehicles, evenly spaced, repeating the same quiet task. Reliability beats haste. Headway, the spacing between climbers prevents resonances. You do not launch as soon as the pad clears. You leave hours between departures, so their small tugs do not add up. A first-year rule might be one departure every 12 hours, with only one vehicle in the most stressed midsection at any time. As the ribbon thickens and damping improves, headway shrinks. 8 hours, 6 hours, maybe less. Mass per climber grows with experience. Vehicles must carry frame, motors, radiators, receivers, and payload. Early craft may deliver only a few tons, later, tens of tons. The live health map sets hard caps by altitude so margins stay wide. One overloaded vehicle that forces a pause costs more throughput than 2 lighter, routine runs. Combine the knobs for a plain example, not a promise. Suppose departures every 8 hours, payload 10 metric tons, and a 10-day ride to GO. About 30 vehicles are strung along the line at any time. The ribbon delivers roughly 30 tons per day to geostationary orbit and brings similar down mass on return. After upgrades, doubling payload or halving headway doubles the flow. Beamed power sets an energy floor that helps with pricing. Physics says you need about 58 megajoules per kilogram to move from Earth's rotating surface to geostationary orbit. Real chains are not perfect. If the end-to-end efficiency from wall plug to traction is 40%, the grid must supply 145 megajoules per kilogram, about 40 kilowatt hours. At 10 cents per kilowatt hour, the raw energy cost is $4 per kilogram. Tickets also pay for hardware, crews, spares, insurance, and financing. Power also limits instantaneous throughput. A climber that needs a few megawatts for days monopolizes a beamline. A site with 20 megawatts of beam capacity might support several vehicles, but only if tracking, interlocks, and cooling keep up. The counterweight hub's down beam helps above the clouds, offloading the ground station. As capacity grows, more beam lines come online, like adding lanes to a freeway. Destinations matter. The elevator is naturally excellent for GEO and beyond. Release a satellite from the upper tail, and it can reach higher or even escape with little extra propellant. Low Earth orbit is trickier. A payload released below GEO shares Earth's 24-hour rotation, but lacks tangential speed for a stable LEO. The practical path is to hand payloads to efficient tugs at GEO and let them spiral down over weeks using solar electric propulsion. It is slower than a direct rocket drop-off, but cheaper over time for bulk cargo. Down mass is an underrated prize. Rockets struggle to bring large or fragile items back. An elevator can lower tons safely. Failed satellites, station modules, manufacturing products, even captured debris. Descent can return some energy through regenerative braking if the beam system can absorb it. When it cannot, the climber still controls the ride by dumping heat on radiator banks. Either way, down traffic is steady revenue and better stewardship of orbit. Scheduling quickly resembles rail control. There are service classes, priority slots for time, critical payloads, standard slots for routine cargo, flexible slots at off-peak hours for lower prices. Passing is planned, so slow vehicles wait in widened bays while faster ones glide by in calmer sections. A steady public timetable builds trust. Customers care that Tuesdays 14:00 departure leaves at 14:00 every time. Maintenance lives inside the timetable. The base publishes weekly groomer windows when inspection cars run, swap worn skins, and splice in fresh modules. Small holds ripple through the lineup, but they are predictable. Way stations stock spares, so a local repair does not require a full climb from sea level. Reliability grows from steady, boring care, and boring is the goal. Price is more than electricity. Operating expense covers crews, energy, consumables, and routine spares. Capital expense covers the ribbon, beam stations, reels, dampers, the ocean platform, and the counterweight hub. Finance spreads those costs over years of service. Early tickets will be high because they carry the learning curve. As factories improve fibers and receivers, as uptime climbs, and as the ribbon thickens, price per kilogram trends down. Insurance and liability are part of the real price. The operator carries coverage for the ribbon, the platform, beam safety, and orbital responsibilities. Customers insure their payloads. Regulators require flight corridors, beam interlocks, and emergency drills. This mirrors commercial aviation and launch operations. Clear rules make cheaper financing possible, which lowers prices for everyone. Finally, uptime is the product you sell. A rocket is an event, an elevator is a schedule. Customers will forgive slow if slow is steady. The operator's dashboard tracks simple public metrics: on-time departures, on-time arrivals, percent of hours the beam is available, unscheduled holds, mean time between splices, health scores by altitude band. Improving those numbers is how the service gets cheaper and safer without hype. In one view, throughput is not about heroics. It is about rhythm, modest speeds, regular headways, honest energy pricing, and maintenance that happens on purpose. Do those things, and a 36, 0-kilometer ribbon stops being a spectacle and becomes what industry needs most: a dependable freight line to orbit. A space elevator succeeds by assuming bad days will come. The design does not chase perfection. It makes mishaps small and local. Think of this as the bad day handbook in plain language. First, the big fear: a snapped tether whipping around Earth. Real dynamics are calmer. Outcomes depend on where a break occurs. If the break is below the geostationary region, the lower segment loses outward pull and falls. Because the ribbon is thin with large area for its mass, air drag spreads and burns most fragments. Any surviving strips splash in pre-cleared water. If the break is near geostationary altitude, the lower part again falls and burns over the ocean. The upper part drifts outward. The counterweight hub fires, thrusters, stabilizes, and waits. If the break is high above geo, tension remains on the lower system. Operators reel in and splice a stored spare. No planet, wide whip, just different cleanup plans for different heights. Prevention is layered. The ribbon is a mesh of many parallel lanes tied by crossmembers, not one strap, so a cut stays local. Lanes run with generous margin, and joints are long overlaps that pass load gradually. Groomer climbers patrol, scan for nicks and hotspots, and stitch fresh filaments over bruises before they grow. Lightning is a headline risk near the base. The lowest section wears a storm sleeve with receptors that invite strikes away from structural fibers. Conductive paths in the ribbon and down the masts give charge an easy route to the ocean. When forecasts turn ugly, departures wait. The safest strike is the one you avoid by pausing. Power hiccups are routine. If a laser or microwave beam blinks, onboard batteries bridge the gap. If power stays out, the climber's friction brakes clamp on sacrificial pads and the vehicle parks. Beam systems have interlocks. If tracking confidence drops or a bird or aircraft strays into the corridor, energy shuts off in milliseconds. Vehicles are built to coast through that moment without drama. Debris and micrometeoroids are the background hazard in low orbit. You cannot armor a sky-length ribbon. You make damage local and repairable. The mesh reroutes load, traffic slows, and a repair car swaps the injured module. The top hub can yaw a fraction of a degree for a day to shift the line tens of kilometers while a forecast conjunction passes, then recenter. Oscillations grow only if you let them. Climbers tug. Day-night heating makes the ribbon breathe. Sensors track motion. Models predict natural frequencies. If a sway builds, base winches tug with tiny phase shifts, tune dampers absorb energy, and counterweight thrusters nudge the line. Climbers vary speed, a few percent to step off dangerous beats. The goal is not zero motion, it is motion that dies. The counterweight hub has its own failure tree. If a thruster fails, the rest carry the load while a service tug delivers a spare. If arrays trip, batteries ride through and departures pause. If momentum runs high after a week of heavy ascents, the hub reels in a little tether and slides ballast inward, then reverses when downbound traffic returns energy. Storms force choices at the base. The ocean platform moves under calmer skies when there is time. If a rare, severe event arrives too fast, the base quick releases. The lower few hundred kilometers drop into the empty ocean corridor and burn or splash in the zone. The upper ribbon drifts outward under the counterweight and waits in safe orbit. Crews reconnect when weather allows. It is the final safety valve, practiced but seldom used. Climber emergencies are designed to be dull. A motor controller trips, brakes hold, the unit reboots. A pump fails. The autopilot commands a slow descent to a service bay. Above the bays, a rescue car tows. All of this is rehearsed for years with cargo before anyone rides. Ionospheric charging bites electronics if you let potentials float. Bonding ties metal parts to the ribbon's conductive paths. Edges are rounded to avoid field spikes. During solar storms, new departures wait, and vehicles in sensitive layers hold at parking altitudes with systems powered and quiet. Beamed power stays safe by procedure and hardware. The beam corridor is a no-fly cylinder managed like a launch range. Radar watches. Interlocks shut the beam down on loss of track, weather triggers, or manual command. If a receiver misbehaves, it fails to a benign load and turns stray energy into heat on radiators, not arcs. Fire is rare in thin air and impossible in vacuum without oxygen, but heat can still ruin parts. Materials are self-extinguishing where air remains. Compartments are isolated. Temperature sensors trip early, and vehicles slow to let radiators catch up. Human error is tamed by culture. Checklists, gate departures, power-ups, and splices. Two-person rules protect critical commands. Simulators let crews practice off nominals until they are boring. Think aviation, not stunts. Environment and public risk are handled openly. Fallen fragments are taped thin. They melt and flutter rather than slam. The ocean corridor stays largely empty during operations. Retrieval boats collect debris. Coatings are chosen for low toxicity and clean burn or easy capture. Regulation, insurance, and transparency back the physics. Drills are required. Base release, beam aborts, rescue tows, storm holds. Public metrics track on-time rates, unplanned holds, health scores by altitude, and repair counts. Transparency builds trust and lowers financing costs, which buys safer margins elsewhere. None of this makes the elevator risk-free. It makes it fail-safe. Pieces fail small. Operators act slowly, and outcomes are controlled. Rockets manage risk by making events short and rare. An elevator manages risk by making events long and dull. In that difference lies its character. Remember one line: the elevator treats failure as a normal mode mesh instead of monolith, breaks instead of falls, quick release instead of catastrophe, and practiced procedure instead of heroics. That attitude, more than any exotic fiber, turns a 36 zero-kilometer experiment into infrastructure. If the ribbon is a 36 zero-kilometer bridge, dynamics is how it moves. The goal is not zero motion. It is motion that stays small and dies away. Picture three movements: sway, side to side, stretch, slow breathing as temperature and traffic change, and twist, a little roll about the long axis. Control means sensing early and nudging at the right time. Start with sway. The ribbon behaves like a long guitar string, held tight by the counterweight. Climbers, gusts, and day-night heating pluck it. Waves run up and down, reflect from both ends, and can add together. If a climber's steady pull hits a natural rhythm, sway grows resonance. Avoid it by never driving one beat for long. The autopilot varies speed and torque like changing your step on a swaying bridge. Stretch is slower. Sunlit sections warm and grow. Shaded sections cool and shrink. The result is a daily tide in tension. Capstans at the base and reels at the top quietly add or remove a few meters to keep average stress centered. Strain fibers and temperature sensors report conditions every few kilometers, so the system acts before anyone feels a change at the grip. Twist is subtle but important. Traction wheels press on wide skins. If forces on one face do not match the other, the ribbon can turn slightly. Symmetric drives keep twists small. Where models predict weak torsional stiffness, usually where the ribbon is thinnest, small fins help in air, and tuned dampers take over in vacuum. Coriolis shows up because Earth spins. A rising climber moves through a rotating frame and feels a sideways push. The ribbon leans a little west during ascent and a little east during descent. The controller expects this. Departure times, speeds, and tiny thruster pulses at the counterweight are chosen so these side tugs cancel over the day. How do you steer a line that long? At the base, a winch tweaks tension and a small lateral tug system on the sleeve mast nudges the foot. Millimeters of reel-in or a few newtons of side pull, timed just ahead of the sway, drain its energy. At the top, efficient electric thrusters add fingertip pushes for minutes at a time. Inside the span, tuned mass dampers sit where models predict big motion. Each is a small weight on a short track, controlled to move slightly out of phase with the local sway. Skyscrapers use the same trick. On the ribbon, these dampers are simple, redundant, and powered from small solar strips on their mounts. Control needs a picture of the line in real time. Strain fibers report stretch. Tiny inertial units report motion. Climbers read visual marks. And radar at the base and hub watches the big arc. Software blends these into the few dominant shapes, the modes, and tells the actuators where and when to act. The answer is found with phase, not force. Pull too early or too late, and you feed the sway. Pull slightly ahead of the motion, and you steal its energy. This phase lead approach works because the ribbon's main rhythms are slow and predictable compared to the controller's reaction time. Scheduling is part of dynamics. Do not send two heavy climbers into the most stressed region together. Time a descent so its Coriolis lean cancels and ascents. Avoid steady beats. No departures on the hour. No cruise speed at a known natural frequency. A touch of deliberate irregularity keeps the line from finding a groove to amplify. Joints and way stations are shaped for smoothness. Long, tapered overlaps avoid sudden stiffness jumps that reflect waves. Widened passing bays sit outside the most sensitive altitudes. Groomer climbers trim loose skins and replace panels that flap. Anything that could rattle becomes quiet. Thermal control is also dynamic control. Coatings that even out sunlight reduce hot stripes that would breathe with each sunrise. Where cycles still drive a slow tide, the reels take it out like a sailor easing a sheet. Short cold soak holds brief pauses to equalize temperature are cheaper than fighting sway later. Debris avoidance uses the same tools. If tracking predicts a close pass in low orbit, the counterweight yaws a fraction of a degree for a few hours, sliding the arc sideways by tens of kilometers. The maneuver is timed between climber transits, and the base adds gentle counter tugs so the line settles quickly. What about surprises and unforecast gust? A beam cut that drops a climber to brakes, or a small meteoroid nick that changes local stiffness. The system treats surprises as short impulses. Dampers zip the first swing. The base and top apply automatic phase-tuned nudges. Within minutes, motion shrinks back to background. Later, a groomer inspects the region. Humans stay in the loop, not chasing the needle. Operators watch simple dashboards, max sway by altitude, tension margin, and a calm score. If it slips, they widen headways, cap speeds, or hold at a way station until conditions recover. They think in sequences and minutes, not joystick twitches. Failure control folds into dynamics. If a lower segment must be quick released for weather, the hub reels a little and fires thrusters so the remaining ribbon climbs to a safe orbit. If a module shows rising strain, traffic pauses in that band while a repair car swaps it. Act early with small moves, not late with big ones. The math modes, damping ratios, observers is elegant, but listeners only need the flavor. The elevator is controllable because the biggest motions are slow, the actuators can push gently for hours, and the software knows the tune. Reels trim tension, thrusters trim position, dampers remove energy, and the timetable avoids feeding resonances. Put simply, keep the line in tension, never drive a steady beat, nudge with the right phase, and let small, smart machines sip away the wiggles. Do that every day, and a structure the length of a planet behaves like a calm bridge that just happens to reach space. A space elevator is not only engineering, it is a legal address, a radio license, a shipping lane, a power plant, and a diplomatic promise. To run every day, it needs simple rules. Location first. The base must sit on the equator. You can anchor on land inside a coastal state or float on a mobile sea platform. Land gives roads and power, but brings local politics and storms. A sea platform can sail to calmer weather and stay under the ribbon as winds push. Inside a country's territorial sea, that country's permits and safety rules apply. In international waters, the platform carries the law of its flag state and follows global maritime rules. Above the water is airspace. When the beam runs, the operator declares a protected cylinder up the sky, like a launch corridor. Notices keep pilots and boats clear. The habit becomes routine. When the beam is hot, the corridor is closed. When the beam is off, it reopens. Then space law takes over. No one owns outer space or orbits. Nations are responsible for the space activities of their companies, so the host nation licenses and supervises the elevator. If the installation causes damage in space, that nation gets the first phone call and recovers costs from the operator by contract. The operator buys deep insurance and keeps generous margins. Geostationary orbit is crowded. Communications satellites live there on assigned longitudes and frequencies. The elevator needs a narrow slot for its hub and counterweight and must coordinate so the tether does not interfere with neighbors. Radios on the hub use cleared bands. If the operator yaws the line for a day to dodge debris, notices go out so nearby satellites can plan. On the ocean, the platform needs a modest safety zone so fishing gear and casual traffic do not snag the sleeve. The zone grows during special operations, first capture of the seed ribbon, a major splice, or a rare quick release, then shrinks again. A clean timetable builds trust with ports and fishermen. Beamed power needs guardrails. Energy at the receiver is high, so the beam is fenced by software and hardware and shuts off in milliseconds if tracking drops or a stray aircraft wanders near the corridor. The ground site behaves like a power station with cooling farms and strict interlocks. Local authorities inspect and certify it. The public learns that the beam lights only when the corridor is closed and weather is green. Security matters because the ribbon is a long, tempting target. The answer is layers, not drama. The base is guarded like a major port. Cybersecurity keeps command links clean. The hub uses encrypted control and has no single kill switch. Any release takes deliberate, multi-person steps. Boats and drones keep a polite distance. Most of the ribbon is unreachable and too thin to harm with small arms. Geopolitics enters when you ask who benefits. One nation may host the base, but the service will carry satellites and cargo from many. Fair access and transparent pricing lower tension. A multinational ownership structure helps. Local jobs at the base, global investors, and an international safety board. Think of it like a canal or an undersea cable. Infrastructure run for many customers. Export controls and data laws show up quietly. Fibers, sensors, and beam hardware may be regulated. The operator needs licenses to move parts and software across borders. Health data from the ribbon can be anonymized and shared for research. Payload data stays private unless customers say otherwise. Environment is part of the permit. The ocean corridor avoids critical habitat. Coatings on the sleeve are low toxicity. Any fallen fragments are thin and burn or sink. Retrieval boats collect what remains. Noise is modest compared to a rocket launch. The grid draw is large but steady and can pair with renewables and storage. Insurance turns law into numbers. Policies cover third-party liability, marine operations, beam operations, orbital operations, and business interruption. Premiums fall as the timetable proves reliable and near-miss counts stay low. Dispute resolution needs a calm forum. Contracts point to neutral arbitration for commercial fights and to agreed courts for injury claims. For cross-border issues, venues are chosen ahead of time so a surprise does not stall the line. Emergency release is planned. The base carries a quick release that can let go of the lowest ribbon in a rare, severe storm. The plan is filed. The drop zone is empty ocean. Recovery boats are staged. After the storm, crews reconnect using a spare kept on the platform. Release means controlled and practiced, not catastrophic. Cyber and radio interference are managed by design. Control links use multiple paths: fiber in the ribbon, line-of-sight radio, and space relays. Commands need two-person authentication and logged procedures. Spectrum for the beam and the comms is coordinated so the elevator does not step on neighbors and cannot be jammed easily. Human factors finish the picture. The base is a workplace with fair hours, safety training, and housing. Sea tours are reasonable. The hub cycles small crews by tender when needed, but most tasks are robotic. A local training pipeline builds technicians and inspectors. The project is not just a machine, it is a small community. Finally, ethics. A space elevator could be a choke point if abused. The cure is sunlight. Publish schedules, prices, uptime, and incident data, and let many launch and satellite operators use the line under the same rules. When customers trust the process, politics calms down. In the end, law and geopolitics are about being a good neighbor. Pick a stable equatorial site, share access, coordinate with air, sea, and space traffic, fence the beam with hard safety, ensure the public, and keep decisions transparent. Do that, and the ribbon will be treated not as a weapon or a trophy, but as a neutral bridge between Earth and orbit.